Okay, so here's a brief review of section 5.2, covering what was really kind of important from that section for us in the long term. It deals with two new segments. We had the perpendicular bisector and angle bisector in 5.1. Now we have the median and the altitude for section 5.2. Now the median is a segment that joins the vertex of a triangle to the midpoint of the opposite side. It does look similar to the angle bisector, but the difference is it doesn't tell us anything about the angle, just as it goes to the midpoint. The altitude is very similar to the perpendicular bisector, except the altitude, let me get the book's drawing of it here, the altitude goes through the vertex and the perpendicular bisector doesn't have to. There we go. So the altitude right here, yeah, here's a perfect example of the book. So the altitude goes from a vertex to the triangle, actually to the opposite side, or a line containing the opposite side. As you can see in this drawing here, it doesn't fit in there. It's too the altitude has to be outside the triangle. More importantly, it goes through a vertex and is perpendicular to it and does not cut it in half. And for some of you, anytime you see a perpendicular, you either assume it's an altitude or you assume it's a perpendicular bisector. The difference is it has to be bisected. So before we jump into the two theorems for this section, I just want to look back real quick at what we did in class this section and talk about how to notice the difference between the two. So forgive me trying to use the marker tool with my mouse because it's not going to be pretty. But we're told in this problem that RSV, so angle RSV, is congruent to angle TSV. Well, here's TSV down here. Notice what they have in common is SV, meaning that SV must be the angle bisector. Because it's created two congruent angles. So SV is our angle bisector. Next, they tell us that RU is congruent to UT. Let's see, can I get my highlighter? That might be easier for me to sketch. Yeah, highlighter. So RU is congruent to UT, which means then for us that U must be the midpoint of that side. That's important for two reasons. One, that means SU is the median, because the median goes from a vertex to the midpoint of the opposite side. And that also means, because that segment, oh sorry, that's actually, no, that's good for that part there. Now the last part is sorting out which one is the perpendicular bisector and which one's the altitude. Well, the altitude has to go from a vertex and be perpendicular to either the opposite side or a line that contains it. So RZ is going to have to be the altitude here, because it's not cutting through anything in the middle. Plus, we already know from the given here that SY is congruent to TY. That means then that SY here is the same length as TY here. And we see our perpendicular line to it at XY, so XY is the perpendicular bisector then. And RZ has to be the altitude. Now in this section we only have two theorems. Okay, the theorem for the medians of a triangle, that's the centroid, and then we have the orthocenter. Now, the orthocenter is all three altitudes. It doesn't have an application, it just exists. If you plot all three altitudes of a triangle or construct them, they'll meet at a point called the orthocenter. So here's a little example of that right here on the computer. So I've got the computer set up so no matter what I do, the altitudes are drawn in. And you can see that point there labeled orthocenter, it forms those. So no matter how I move that around, it could be inside, outside, wherever. It could be all over the place. But all three of the altitudes, altitude here, and altitude here, they all go through a vertex and are perpendicular to the opposite side. That ends up being the orthocenter. And if I make this obtuse, you can see here's the altitude outside the triangle, right here, perpendicular to that line that contains that side. The other special point is if you have all the medians. So if you have all the medians, they meet at a point called P, in this case. And there's a special theorem that says that the distance from the centroid, to the vertex is 2/3 the length of the whole segment. That's the relationship. And you can see right here, AP is the whole segment. AP is the short segment. A to P, AF is the whole segment. And if I do AP divided by AF, I get 2/3. Same thing over here. BP is the short segment. BD is the whole segment. BP over BD is 2/3. CP is the part segment. CE is the whole segment. CP over CE is 2/3. But in class, you'll note that I said, hey, don't think of it that way. Think of it and said this. This segment here is twice the length of this one. Oops. So there are two, spot here, and then full spot here. So that's what it ends up creating for us is twice the length from here to here. So what you might be able to describe it in words is the centroid creates a segment that is twice as long from the vertex of the centroid as it is from the centroid to the side. That's what's happening. It's 2 times as long from here as it is to here. And no matter how I move that around, that always holds out that 2/3 business. The other thing that's special about the centroid is it's the center of mass. It's the part where you could balance that figure at wherever it's at in the drawing. So let's look at some problems then. So in this drawing, we are told that AU is 16, which they've already marked for us. Told that BU is 12, which they've already marked for us. And that CF is 18, which they didn't mark for us. Now the key to this problem is understanding I have the centroid at point U because all of the sides have been bisected by a segment that goes from their opposite vertex. So now for us to find our missing lengths, we have to use the centroid theorem, which says that this length here is 2/3 the length of the full segment. Now again, I don't like the 2/3 part. I prefer to think that it's been cut into full thirds, and this is twice the length of that guy. So if this is 12, this is really 6 and 6. This is 6. If this guy's been cut in half, he's 8 and 8, and this is 8 from U to D. And then CF is 18. Well, I'm going to divide that into thirds. That means it's 6. So CF is 6, and double that is 12. And that adds 18 together now. So now I can just start filling out lengths. UD is 8. EU is 6. CU is 12. AD is the full length. Well, 16 plus 8 is 24. UF is the shorter length. Well, if that was 12, half of it is 6. And BE is the full length again. Again, this is 12. So this is 6 and 6. That makes that 6. The whole length then is 18. Same thing happens then on 7 through 12. Again, this time they told us U is the centroid, and they've marked in our stuff. So I don't even think about it anymore. I just know this is half the length of this guy. So if this is 12, this is 24. This is the longer one, so he's double the length of this guy, so he is 4.5. And then EM is that full length, so if I take 21 and divide it by 3, I get 7. Shorter one, 7, double that's 14. And now I can just start filling in the missing sides. So CU is 24. MU is 7. CK, that full length, is 24 plus 12, so 36. JU is the shorter one of the two, so that's 9. It's half of it is 4.5. EU is 14, since it's 2/3 of 21. And then JD is the full length here, so 9 plus 4.5 is 13.5. And that's basically it. The altitudes create, again, the orthocenter. The altitudes create the orthocenter. But really that has no purpose for us. It just exists. It's the medians that are important.